Very good evening to all of you and welcome to the session. So today we are going to talk about geometry, and basically when you begin with geometry, the very important thing that you should be aware of is that geometry has a very close connection with percentages. So when it comes to the application of percentages, geometry sees its significance. In the first question itself, here you can see that the question talks about percentages. So what kind of an application that percentages gives us to make this question very convenient for us to solve? So the question goes like this: the radius of a sphere is increased by 30%, and we have to find out the percentage increase in its surface area. Now you might think that I have to create a lot of formulas for the surface area, solve the question accordingly, but actually speaking, the question has a very simple logic of utilizing that percentages can give us the solution very quick. How? So what we say here is that if we talk about the radius getting increased by 30%, which we can represent by saying that, let's say capital R is the new radius after the increase. So it has to be 1.3 times the old radius. Now, surface area, the formula of surface area, that is not actually important here. What is important is what variable does it use? It uses square of the radius. So, if I just square both sides of this equation, what do I observe? The new radius square is 1.69 times the old radius square, which is nothing but the percentage increase getting reflected in the surface area. So what we can say is the new surface area will be 1.69 times the old surface area. Why? Because the other constants do not actually affect the percentage change. The variables only are going to affect the percentage change, which means what is the percentage change that is getting reflected? It is 69% increase. So the question was, what is the percentage increase in its surface area? The answer is 69%. So this is what I was talking about, percentage playing a very important role in solving the questions of geometry. Now the same thing you will realize in the next question as well. The information given in this question also talks about, some percentage coming into picture. And there is also a numerical value coming into picture. What does the question say? The length and breadth of a rectangle are 24 centimeter and 15 centimeter respectively. If the length is increased by 20%, here there is a percentage component. Also, we are told that breadth is increased by 1.5 centimeter. That is a numerical value, not given in percentages. Question then talks about what is the percentage change in the area of the figure. Now again, a very important application of percentages comes in. That is, whenever we talk about percentage change of a quantity which is made up of product of two things. For example, here the area is product of length and breadth. So the percentage change in length, the percentage change in breadth, and the percentage change in area, they follow a particular relationship. What is that relationship? That relationship says that if we talk about the percentage change in length as P, of course this value is in percentages, do not forget that. The sign of this value is very important in the formula. The formula I'll just tell you. So the sign of the value of P will be dependent on the fact whether it's a percentage increase or a percentage decrease. All right. So P is basically representing what? The percentage change in the length. Similarly, let us talk about Q, which represents the percentage change in breadth. Using these two values, we are going to find out R, which represents percentage change in area. Now, the formula which connects these three variables is P plus Q plus PQ by 100 is equal to R. Please do not forget that while using this formula, it's very important to be careful about the sign. By sign, what we precisely mean is, if it is a percentage increase, it has to be given a positive value. If it is a percentage decrease, it has to be given a negative value. Now, when we read the question, everything has to be in the percentages. The numerical value needs to be converted into percentages. So, for example, the question here said that the length and breadth of a rectangle were 24 and 15. The length is increased by 20%. This is important. So, if length is increased by 20%, which means the value of P is plus 20. The breadth is decreased by 1.5 centimeter. That's a numerical value. What is this decrease as a percentage? 1.5 is what percentage of the original value 15? That's simple. It's just 10%. But what is this 10%? Is it an increase or a decrease? It's a decrease. So I need to call it as minus 10. Now, the job is very simple. You have to just put these values of P and Q in the formula and find out the value of R. If this value of R comes out to be positive, it indicates that area has increased by that much percentage. If this R comes out to be, say, negative, it indicates that the area has decreased by that much percentage. So let's see. If I substitute these values here, it's going to be 20 minus 10 minus 20 into 10 divided by 100 is equal to R, which comes out to be 10 minus 2, that's 8. It's a positive value, which indicates that the percentage change in the area is a positive one, which means the area has increased by 8%. So positive indicates percentage increase. This 8 is not a numerical value, it's a percentage value that we have obtained. So in both these questions that we have taken, we could realize that percentage plays a very important role when it comes to its applications in geometry. In fact, percentage has huge amount of applications in other chapters also, like TSD, mixtures, ratios, alligation. So geometry also has a very huge connection with the basic fundamentals of percentages being clear. So we have used two very basic concepts of percentages in the first two questions. Let's move ahead. Now this question is a pure geometrical question based on a three-dimensional figure. So let's read the question. The surface area of a cubical room is numerically equal to its volume. So here, of course, what is being tested here is, are you aware of the formula of surface area of a cube and volume of a cube? Of course, these two formulas are very, very simple. So what is surface area of a cube? It is 6 times of a square. What is this a? The side of the cube, or we can say the edge of the cube. What is the volume of a cube? It is a cube. So if we equate these two as per the question's language, what do we get to know? The dimension of the side or the edge of the cube. After finding that, the question says, if you want to keep a rod which is having a length of 10, will it be possible for you to do that or not? Now, this question needs a little bit of visualization. If you just imagine the room in which you are sitting, so just imagine that it's a cubicle room. Which is the longest rod that you will be able to place in the room? Obviously, the longest rod which is available to be placed, or the space which is available to be placed, is the one that starts from one corner of the roof to the opposite corner of the floor. That is the longest diagonal that we have. So technically we call it as the longest diagonal, but in a layman language, it's basically the longest rod that you can fit in that room. So that longest rod has to always start from one corner of the rooftop to the opposite corner of the floor. That's exactly what is the visualization needed in the question. So the longest rod that we are talking about is the one that starts from here to here. So the question, of course, talks about will it be possible for us to place that rod or not? The answer has to be given as a yes or a no. So how do we proceed to solve it? Of course, we start by what is given in the question, which is helping us to find the length of the side or the edge of the cube. That is, the surface area is equal to the volume, which means the value of A is simply 6 units. Now, what is the longest diagonal of a cube? Though it's a simple application of Pythagoras Theorem getting applied 2 times, but of course we recommend that you should remember it as a formula rather than deriving it in the exam, right? So the simple formula for a cube to have the longest diagonal, where is that longest diagonal? Starting from one corner of the floor, going to the opposite corner of the roof. So this is what the longest diagonal has to be, as a straight line, of course. So the longest diagonal has a simple formula, √3 times of A. So basically, if you talk about a cuboid having a longest diagonal, it's going to be L square plus B square plus H square, the sum completely inside a square root sign. For a cube, because length, breadth and height are all same as A, so it comes out to be 3A square square root, which is of course √3 times of A. So if I just substitute A here, it's √3 times of 6, which is the longest diagonal that we have. Roughly, what is this value? 6 multiplied with 1.732, so we are taking it as roughly 1.7, which is 10.2 units. And of course, it is more than 10. That means the space which is available to me, that is the longest diagonal, is more than the rod that you are trying to place. So since the space available is more than the length of the rod, of course, it's possible for us to place this rod inside this cube. So the answer to the question is yes, it is possible. So this was a question which was purely based on the formulas of surface area and volume of a 3-dimensional object, very simple 3-dimensional object, that is a cube. Let's move to the next question now. So this question is from the concept of the triangles. And which concept of triangles? The very basic concept, which is taught as the first concept that you deal with when you talk about triangles. And that first concept is always done like a practical experiment, that if you are given 3 sticks, will you always be able to create a triangle out of it? The answer is no, it depends. What does it depend on? It depends on a condition getting satisfied by these 3 sticks length. What is that condition? The sum of any 2 sides has to be greater than the third side, right? But here, the question isn't talking about the 3 dimensions. In fact, the question is only talking about the perimeter of the triangle, which means whatever are the 3 sides of this triangle, their sum is known to me. All right. So majority of the people think that whenever it comes to questions based on a triangle, that how many triangles are possible, it is always something to do with the number of triangles being possible based on the fact that that property which I just talked about, that is sum of any 2 sides has to be greater than the third side, will come into picture. But that is only possible when I know the 3 dimensions of the triangle, the 3 sides of the triangle. Here, the question's language is slightly different. So this one says that we just know the perimeter is 14. So how many triangles are possible? It's not going to be possible to solve this question unless a very important information which is there in the question is given to you. That is integral sides. The sides are not known to us, but we are at least told that all the sides are going to have integers as their dimensions, which means now it is going to be possible for us to solve the question because there will be limited number of combinations possible. So please mind it, if this word is removed from the question, the integral sides, that means I can go into decimals and then the question will have infinite possibilities, which is not going to be possible for you to solve as a question. So you will give the answer as none of these or cannot be determined. But here, since that is there in the question, so of course it will have finite number of combinations possible. That is why the options are also all finite numbers. So how do we solve this question? The logic behind solving this question, if you go by the logic, is that the perimeter is 14 and of course that property has to come into picture, that is the sum of any two sides. Any is important. Sum of any two sides is always greater than the third side, which means if we talk about the three sides of the triangle as say A, B and C, finding the number of triangles basically mean that we are trying to find out how many values A, B and C can take. Keeping in mind that sum of any two sides has to be greater than the third side. Now, any is very important here. This rule is applicable for B plus C being more than A. This rule is also applicable for A plus C being more than B. Also, there is another condition provided in the question, that is the perimeter is 14. Keeping all this in mind, how many values A, B and C can take, and integers only. So where do we start from? It has to be finite number of combinations and the options are also reflecting that it's not going to be too many of them. So how do we start? Start with the half of the perimeter not being assigned to any of the sides. Why? Because if I decide to give 7 to any of these sides, the other two will have a sum of 7 to make a perimeter of 14, which will violate this condition that the sum of two sides had to be strictly greater than the third side. It is not allowed to be equal to the third side. So, which means that I will not be able to allocate 7 or anything more than 7 to any of the sides. So, what is the maximum possible value that we can give to any of the sides here? That is 6 units. So, if I give 6 units to this one and 6 units to this one, then the third one to make the perimeter as 14 will have 2. Next is I'll just gradually bring it down. I'll have a combination of 6 and 5 with a 3 to make the perimeter again as 14. Next combination is 6 and 4 with a 4. Now look carefully that we are done with the combinations of 6 and 6, 6 and 5, 6 and 4, 6 and 3, 6 and 2. 6 and 1 is not going to be possible because that will make the third side as 7. So all the combinations with 6 are already done. Looking at 5, 5 and 6 is already there. The only one which is missing is 5 and 5 with the third one being 4. Again, scanning through all the possibilities, there is no more available. Why? Because 5-6 combination is already there, 5-5 is there, 5-4 is there, 5-3 is already there, 5-2 and next one's not possible. 4-6 is already there, 4-5 is already there, 4-4 is already there, 4-3 and downward not possible, and so on. So these are the only combinations which are possible, which means there are only 4 such triangles possible. But remember, that's a very important thing to notice, that if this word is missing in the question, then of course the answer cannot be found. If this word is there in the question, then only it will have finite number of possibilities, which is number of possibilities coming out to be 4 for this question. So this was a question that is based on a very basic concept of triangles, which will always be very important to solve basic questions that talk about dimensions of the triangle given, or its perimeter being given, anything to do with the sides being provided to you either individually or in the form of the perimeter, or an information of the type that the triangle is isosceles. All such questions will have this as the base of solving. Let's move ahead. This question is talking about a very basic concept of circles now. It says, what is the maximum distance between two parallel chords, parallel is very important here, of length 6 and 8, respectively in a circle of diameter 10 centimeter. So what are the informations given to us? The diameter is 10 centimeters, which means radius is of course 5. There are two parallel chords that we are talking about of the length 6 and 8 respectively. The question is talking about maximum distance between them. Now, the only basic visualization which is required for moving ahead with this question is, when are the two chords going to be having the maximum distance between them? Of course, when one of them is on one side of the center and the other one is on the opposite side of the center, which means if this is suppose the center of the triangle, center of the circle, then of course I have to place one chord above the center and one chord below the center as a visualization. So if we decide to take this as one of the chords and this as the other one, we are told that they are parallel to each other. One of them has a measurement of 6 centimeter and the other one has a measurement of say 8 centimeters. We're also told that the radius of the circle happens to be 5 centimeters. So let's visualize this. Now I'm sure it's very obvious how to proceed with the solution. A very famous theorem for circles, that is, when we drop a perpendicular from the center of the circle to the chord, it bisects the chord. That's it. So if this entire measurement is 6 centimeters, then this much is 3. Let's talk about this much only. Similarly, if this entire is 8, then this much happens to be 4. So Pythagoras theorem plays its role now. Pythagoras theorem tells us that there is a very famous Pythagorean triplet which sees its importance in a lot of questions when you talk about right angle triangles. And that Pythagorean triplet is 3, 4, 5. We see that this hypotenuse happens to be 5 and this is 4, so this has to be 3. Similarly, in the other right angled triangle which has got created here, the hypotenuse is 5, this is 3, so this has to be 4. That's it, we are done with the question. What is the distance between the two parallel chords? It's 3 centimeters plus 4 centimeters, that is 7 centimeters is the answer. Now the interesting question that can get created here as another one based on the same question is, what is the minimum distance between such chords? So the concept is pretty simple. You kept the two chords on the opposite sides of the center to create the maximum distance. If the question is asked for the minimum distance, you will prefer to keep the chords, of course, on the same side of the center. In that case, I don't have to change the diagram. I have to just visualize it that in that case, I will not be adding 3 and 4. In fact, I will be subtracting them. So, if the same question comes for the minimum distance between them, the answer will be 1 centimeter. So that's like an extra question that we have solved here because it's completely based on the same diagram. So that was a very basic property of circles, that is, a perpendicular drawn from the center to the chord bisects the chord. Let's move ahead. This question is also based on the concept of right-angled triangles, and the concept of Pythagorean triplet definitely comes into picture whenever we talk about right-angled triangles. So this question says that ABC is a right-angled triangle with BC as the hypotenuse. The length of AB and AC are given as 15 and 20 respectively in kilometers. What is the minimum possible time which is required in minutes to reach the hypotenuse from the point A? You are told that speed is 30 kilometers per hour. So this question is just a basic question based on two basic concepts, that is right-angled triangles, Pythagorean triplet, and the basic concept of time, speed, distance. So what do we have to visualize in the question? Just a right-angled triangle. You are told that in this right-angled triangle, BC happens to be the hypotenuse. So if I call this as B and this as C, this happens to be A. Question said the length of AB and AC are 15 and 20 respectively. So this is 15 kilometers, this is 20 kilometers. So do we have to actually solve for the hypotenuse? The answer is no. It's a famous Pythagorean triplet again coming up in picture. Length of AB happens to be 15 and length of AC happens to be 20, tells you that the hypotenuse has to be again derived from the famous Pythagorean triplet, that is 3, 4 and 5. So any multiple of the Pythagorean triplet 3, 4, 5 also happens to be a Pythagorean triplet. 15 is 5 times of 3. 20 is 5 times of 4. So what we have to have in the hypotenuse is 5 times of 5, which is 25 kilometers. Now the question said you have to travel from A to the hypotenuse. So that means you are talking about a perpendicular dropped from A to the hypotenuse, because that is the shortest distance that you will travel. How do we find this perpendicular distance? Of course, again very simple. The area of a right angle triangle can be expressed in two combinations here, with base as 20, height as 15. The other one is base as 25, height as h. They both have to be equal. So area of the triangle can be expressed as half into base into height, or it can also be expressed as half into base into height, which tells me that this h is nothing but 12 kilometers. So the distance which needs to be traveled is 12 kilometers. Now the basic concept of TSD is coming into picture. The distance to be traveled is known to us. The speed at which we are traveling is 30 kilometers per hour. So how much is the time required for traveling this distance? But the answer is to be given in minutes, which means distance is 12, speed is 30, but to convert it into minutes, we multiply by 60. So the answer comes out to be 24 minutes. So a very simple question which can be solved very quickly, because it's based on the basic concept of Pythagorean triplets and the basic concept of TSD. So geometry has this typical thing that it sees a lot of combinations with other topics, like percentages coming into picture. A visualization, of course, is always going to be an important element when it comes to geometry. TSD coming into picture with geometry, those basic concepts getting clubbed in one single question. So let's move ahead. This one will now look like a similar question that we have already talked about. How many triangles possible? So as I've already told you that whenever the question talks about how many triangles possible, it is always going to do something with that basic criteria of creating a triangle, that is, sum of any two sides has to be greater than the third side. Here you are already told that the dimensions of two sides are given as 17 centimeters and 7 centimeters. The third one is of course missing in the question, and that's exactly what we have to count. How many values that third side can take will decide the number of triangles possible. Again, the important word which is never to be missed in these categories of questions where they tell you to count the number of triangles possible is integer. That's again provided in the question. All right, so let's read the question. 3 dimensions of a triangle are integer centimeter long, which is very important. 2 of them are 17 centimeters and 7 centimeters. How many different combinations are possible for the third side? So the idea is pretty simple. We again decide that the third side, let's call it as x. All 3 in centimeters, of course. Now, sum of any 2 sides has to be greater than the third side. Sum of any 2 sides has to be greater than the third side. Right? So, sum of any 2 sides has to be greater than the third side. Now, this is kind of redundant. We know that 17 added with anything is of course going to be more than 7. These 2 are important. The first one tells me that x has to be less than 24. The second one tells me that x has to be greater than 10. Using the information that only integer values are allowed, so the range comes out to be more than 10, less than 24. Integers tell me that you have to start with 11, end at 23. So how many values x can take from 11 to 23? These are going to be the answers available for us to decide the number of triangles. All right, because whatever is the value that x is taking is telling me that how many such combinations are possible, and that will automatically answer how many triangles are possible. So that's going to be 13 such triangles. So the answer is 13. So again, a very basic question that talks about the number of triangles possible based on, again, the same important information that sum of any 2 sides of a triangle is always greater than the third side. So let's move ahead. This question is talking about the angle bisector theorem getting applied. So let's read the question first of all. In the triangle PQR, the dimension of PQ is given to you as 10 centimeters, QR is given to you as 8 centimeters, and PR is given to you as 6 centimeters. So S is a point on QR such that PS is the angle bisector of the angle RPQ, which means the angle bisector theorem has to play its important role for solving this question. Let's visualize what the question is going to look like in terms of the triangle getting constructed here. So we should always notice in any question where the 3 sides of the triangle are provided, that is it making a Pythagorean triplet? If yes, then of course it's going to be a right-angled triangle here. So that is one very important observation in this question, that it's going to be a right-angled triangle for sure. Why? Because the dimensions are 10, 8 and 6, which is a famous Pythagorean triplet. So of course, PQ happens to be the hypotenuse here. And the question has given you the information that PQ is 10 centimeters, PR happens to be 6 centimeters, and QR happens to be 8 centimeters. The question then said that S is a point on QR such that PS is the angle bisector of the angle RPQ. So the angle bisector theorem tells you that if this angle got bisected, then the ratio in which 6 and 10 are, that is the arms of the angle, has to be the same ratio in which the opposite side is getting cut by this angle bisector. So the ratio of these 2 sides or the arms of the angle is 6:10, which in a simplified version is 3:5. So this ratio also has to be 3:5. But we already know that the total is 8. So of course, this has to be 3 units and this has to be 5 units. Now moving ahead in the question, it says that the angle bisector of PQR intersects PS at W, which means now we are talking about this angle bisector coming here at the point W. And the same angle bisector theorem again gets implemented. The arm in which the angle which is getting bisected is having a ratio of 10:5, that's 2:1. So these two are also going to be in the same ratio, 2:1. But be very careful, the question is talking about the ratio of SW to WP. So the ratio of SW to WP is going to be 1:2. So that is the required answer. And it was simply based on the concept of angle bisector theorem getting applied 2 times in this question. So angle bisector theorem or basic proportionality theorem, these are some typical theorems which definitely needs a quick revision when you are preparing for geometry, because these are the theorems which might be difficult to prove but very easy to apply. The only thing which is required is you should be able to understand that what does the theorem say, how do we apply it in a question, how do we realize that, this is how the theorem gets implemented here. So that basically doesn't require the knowledge of having to go through the proof of that theorem. It just needs a basic understanding of how the theorem gets implemented here. So let's move ahead. This question is going to talk about the basic concept of coordinate geometry coming into picture. So whenever a question talks about, a region being enclosed under a particular, the function provided to you in the form of x and y, where modulus is involved, the only thing that you need to understand is that this is going to have 4 possibilities here. Why 4 possibilities? Because x can be a positive number or a negative number. Similarly, y can be a positive number or a negative number. So the 4 possibilities that get created here are x plus y equal to 2, a line getting represented. Similarly, the other versions are going to be minus x plus y equal to 2, or x minus y equal to 2, or minus x minus y equal to 2. Now these 4 lines are not necessarily to be plotted. With just the understanding of the one line where both are positive, we can have an idea of how to solve the question. So if we just understand that the line that is representing x plus y equal to 2 is this line, which joins 2 points. This point is basically 2, 0, and this point is 0, 2. That is how we plot a particular line in coordinate geometry. Now the others are going to follow in the similar fashion, and they will follow the rule of symmetry, right? Which means if I have to find out the area enclosed, I can just focus on this area and make it multiplied by 4, because that's going to be 4 times appearing in the question. So what is the area of that triangle? Half into base into height, which means it's going to be 2 square units. But as I said, it's going to get repeated 4 times because there are 4 such regions. So the complete area that the question is looking for is going to be 8 square units. So the answer is going to be 8. So this was a question that is based on the basic concept of coordinate geometry, which tells you that whenever a question comes with mod appearing in the question, we can always go for the symmetry coming into picture, which makes it convenient for us to solve the question in just first quadrant and follow the symmetry for other quadrants wherever the region is possible to be drawn as per the function provided. So basically we have touched the basic concept of geometry getting connected with percentages, geometry getting connected with TSD, geometry getting connected with coordinate geometry as one of its subtopics, and some theorems which are very commonly used in geometry, and of course, as I said, their proof might be difficult, but their application is very simple. You just have to have a clear understanding of how the theorem gets applied in the question, and then of course, when you have to practice it so much that when you look at a question, you should be able to answer yourself immediately that this is the theorem which is going to solve this question. So geometry is one topic which definitely talks about a lot of practice. Practice is the only key to geometry. Visualization is very important for geometry. Approximation is very important for geometry. So if you want to excel in this topic, these 3 key components are very much required. Practice the questions, be able to visualize the question correct, make some approximations in terms of the dimensions provided and make a clear visualization of what the figure is going to look like. And then, of course, the main important theorems whenever it comes to a technical question is always going to be important. So this brings us to the end of the session. Thank you, everyone.